Section 7.6, Ideal Gas Law. Calculate the number of moles, moles, pressure, volume, or temperature in a sample of a gas using the quantities of the other three. Okay, so the ideal gas law kind of combines all of our laws. It's also known as the combined gas law, but I want you to go ahead and use the terminology ideal gas law. So it's got a combination of Boyle's law, Charles's law, Avogadro's law, and it is PV equals nRT. So it draws our relationship between pressure, volume, amount of a substance, and temperature to give us this value, an R value as it's commonly known, a constant, which is 0.08206. Now the units for this are a little bit tricky, but I think the units are great to know. Reason being is they combine all of the different units that are for all of the different values. So the ideal gas law, the ideal gas constant has units that are liter atmospheres over moles Kelvin. I think that this is really helpful because if you ever encounter a problem where you're told something like the pressure is 760 torr and you're ready to do that calculation, you say, oh, I got the pressure, I got the volume, I got everything. Well, as soon as you start to plug it in, if you have learned this value right here, liters atmospheres per mole Kelvin, then you're going to say, wait a minute, my pressure needs to be in atmospheres. I can't be using my pressure in torr or millimeters mercury or anything like that. It has to be in atmospheres. So then you're going to kind of trigger a process in your brain where you say, got to convert it. Okay, so I would recommend learning this ideal gas constant just because it engages you in the process of solving these equations. I'm going to give you this value, but the more that you are comfortable with it and the more that you understand it, the better off you're going to be whenever you're solving these sorts of problems. Okay, so the ideal gas law approximates the behavior of real gases, and this is a term that's kind of important, but real gases, and works exactly only for hypothetical ideal gases. The ideal gas law can be used to calculate P, V, T, or N of a gas sample when the other three values are known. So you can solve for N if you know P, V, and T. You can solve for T if you know P, V, and N. It can be used to calculate changes in temperature, pressure, volume, and number of moles when the others are held constant as well. So you can observe a change. For instance, something is heated up, and so you'd be able to say, okay, well, what is the change in volume based on this change in temperature? So here we've got a question where we're going to use this ideal gas equation. I always like to just write it out, PV equals nRT. Manipulating this ideal gas equation is something that's really helpful to do, but we'll go ahead and work through the problem and then figure out what's the thing that we want to isolate. So this question asks us to calculate the volume of N equals 1.63 moles of CO2 at 295 Kelvin. So T, 295 Kelvin, and P equals 1.14 atmospheres. Okay, so what I need to do is I need to isolate volume because that's what I'm solving for. So I'm going to go ahead and do my rearrangement of this equation to say V is equal to nRT over P because I divided each side by P. And there we go. Okay, now what else do I need to know? Again, I always like to write my values out. I'm going to write this as V is equal to N, 1.63 moles. R is equal to 0.08206 liter atmospheres, ATM, mole Kelvin. T is 295 Kelvin, and pressure is 1.14 atmospheres. All right, so this is just a plug and chug. So 1.33 times 0.08206 times 295 equals 32.1962 divided by 1.14. The volume of this sample is 28.24. And if you're just in a plug and chug mentality, let's go ahead and get rid of some units so that we know what units that we're working with. So if we look back at our solved equation, moles will cancel. Kelvin will cancel. Atmospheres will cancel, and we're left with liters. So that's all there is to that. Calculate the pressure of a 0.00789 mole of chlorine gas, Cl2, that occupies 891 milliliters at negative 15 degrees Celsius. Okay, so this has two unit conversions that we need to take into consideration, and we're calculating the pressure. So again, our equation PV equals nRT. Let's rearrange that. And this is a simple rearrangement. P is equal to nRT over V, because we divided each side by volume. Okay, now the first thing, we have our N value. And I'm going to go ahead and write this equation out. P is equal to 0.0789 moles times my R value, 0.08206 liters atmospheres, mole Kelvin. Temperature. Okay, T. This is our first conversion that we need to take into consideration. This is negative 15 degrees Celsius. Okay, we need our temperature to be in units of Kelvin. So anytime you are working with anytime you are working with degrees Celsius, what do you need to do? You need to take that temperature and add 273.15. So I'll say negative 15 plus 273.15 equals 258.15. Now, in the event that, or before I continue really with this, in the event that you maybe make that mistake and you say, oh, well, I think that I need to subtract 273, well, think about it this way. That would give you a negative value. And chances are you're not going to have a negative, or you might not have a negative value in this. So just be careful whenever you're doing this sort of calculation and you're doing that sort of conversion there. Okay. The last thing that we need to solve is our volume, 891 milliliters. This is one of those conversions that I like to do on the fly, and I just like to write that as 0.891 liters. I don't like to set it up, I don't like to dedicate the time and spend the time setting this up for a involved conversion. I just like to know, or I kind of worked through and committed to memory that 900 milliliters is 0.9 liters. 500 milliliters is 0.5 liters. So then I know 0.891 liters. I saved a little bit of time by not having to do that. And so now what I'm going to do is my moles are going to cancel. My Kelvin is going to cancel. Liters are going to cancel. And my units are going to be in atmospheres. So I'll plug this in, 0.0789 times 0.08206 times 258.15 divided by 0.891. Pressure is equal to 1.87. I'll call that 1.88 units, atmospheres. And that's all there is to it. All right, I hope this is helpful, and I'll see you in the next section.